These are some examples I have from chapter 20, and what I'm going to end up doing is go through them. I usually like to solve them step by step. I think that it would take me too long, and I don't think people would pay attention. So, example 1, find the magnitude and direction of the electric force on a plus 2 microcoulomb, that's 2 times 10 to the negative 6 coulomb charge, the following situation. You've got the 2 microcoulomb one here, you've got a positive 3 microcoulomb one here, they're 2 meters apart. So this is the simplest application I could think of Coulomb's law. So K times charge 1 times charge 2 over the distance squared. So this is going to be 0.0135 newtons. Now you might say, well, how do I get the direction? Well, you could put positives in here and realize that positive answer to the force is going to be a repulsion, and negative answer to the force, if you have a positive times a negative, would be an attraction. I don't do that. I just use the absolute values of these, and I look at the scenario to figure out that these are going to be repelled from each other, and therefore this charge will have a force to the left, this charge would have a force to the right. The other thing to think about is if I asked you for the force on this charge, note that now it would be the same magnitude of force, but it would be directed to the right. So for part B of this example, it says find the location that a negative 5 microcoulomb charge would need to be placed to result in no net force on the plus 2 microcoulomb charge. So if we think about it, if we put a negative charge over here in this region, it's going to be attracted to the right by this, and it's going to be attracted to the right by this. So that negative can't be over here. If I put a negative in this region of space, it's going to be attracted to the left by both of these charges. So that would not result in zero net force. So it's got to be somewhere in here. We can tell that this negative 5 microcoulomb charge would be somewhere closer to this charge because it's a weaker magnitude. So somewhere towards this side of this 2 meter distance. So we need to think about, and the easiest way for me to think about that is we needed a net force of 0.135 newtons to the right. So in this particular case then, that question was a little different. So we want this to have no net force on it, sorry. So in that case, I need the negative charge to be somewhere over here. So I'm just going to apply Coulomb's law again, but with these two charges. I know the amount of force that I need because it needs to equal the amount of force that's here, and I can figure out the distance. So this came out to 2.58 meters. So it says that the negative 5 charge would need to be 2.58 meters to the right of this charge. That would have the same effect in terms of the amount of force as the plus 2 and the plus 3 would have. So I didn't say that very well. Sorry about that. I'm going to go through example 2, then I'll pause for just a moment. So example 2 says find the net force and direction on the plus 2 microcoulomb charge in the diagram. So this is the diagram here. We've got plus 1, plus 2, and negative 3 microcoulombs, 25 centimeters and 50 centimeters. So in this case, this is a vector problem. So the force between 1 and 2, I could use Coulomb's law equation. Notice it's 50 centimeters, that's 0.5 meters. So I do want to use standard units in here, so no microcoulombs and no centimeters. It's got to be coulombs and meters. So I get this force, and on this plus 2 microcoulomb charge, the force would be to the left caused by this. Here, the force on this plus 2 microcoulomb charge will be down due to an attraction caused by this. So when I plug these numbers in, I get this amount of force down. So I get an overall force down of this amount, an overall force to the left of this amount. Notice that this is a lot more, but that's because this is 3 times the charge and it's twice as close. So 3 times the charge in this formula would result in 3 times the force. Twice as close would result in 4 times the force because the distance is squared. So 3 times the charge and twice as close means that this should be 12 times this amount. And I bet if you multiply 0.072 times 12, you get this. At any rate, to find the resultant, I use some old-fashioned trigonometry, which you should be pretty good at this point. So Pythagorean theorem to get the resultant, inverse tangent to get this. Make sure you're in degree mode, not radian mode. So overall, I have 0.867 newtons at 4.76 degrees west of south, or 85.24 degrees south of west. So those are examples 1 and 2. Third example, and in this example, you've got 4 charges plus 4 here, and 2 negative charges, negative 2 here. So this is labeled 0 meter, 1 meter, 2 meter, and so forth. So the question is to find a location where the electric field caused by the 2 charges is 0. So I've got these at 2 different spots, like I said, and I'm going to assume this is 3 meter, 4 meter, 5 meter, 6 meter, 7 meters. So that's kind of interesting. I didn't write that down very well, and so I think I need to do that. So I'm going to do this. It'll be a text box. Don't really need that. So I'll do something like 4, 5, 6. So put those on top of there, so at least we know, where they are. Okay. 7, 8, 9, and so forth. So we want to find a location along here where the electric field is 0 caused by both those charges. So the first thing I want to do is think about the direction of the electric field caused by each of those 2 charges in each region of space. So I'm calling this region 1, which is to the left of both charges. Region 2 is in between the charges. And region 3 is to the right of both charges. So in this first region, if you understand that electric field lines point away from positives and toward negatives, then we know that the electric field caused by these positive charges is going to be pointing to the left. And I've drawn that in red, and I've circled that +4 in red. The electric field caused by these 2 negative charges, which I've circled in purple, is pointing to the right. So in this region, the field pointing to the left must be larger than the field pointing to the right. And that's because the field pointing to the left is caused by more charge, and those charges are closer. So there's nowhere in this region where you could have 0 net electric field. In this region, depending on where you would choose a location, both fields caused by these charges would be pointing to the right. Now, this has less charge than this does, but if you're getting close, very close to this -2, the electric field caused by that -2 would actually end up being larger than the electric field caused by the +4. So it doesn't really matter what size these 2 arrows are. The point is in this region, they're both pointing to the right, and so again, I can't have 2 electric fields. In this area, the electric field caused by the -2 would point to the left toward the negative charge, and the electric field caused by the +4 would point to the right away from these positive charges. So they're pointing in opposite directions, and since the -2 is closer than the +4, it's likely that the effect caused by the closeness will be counteracted by the effect of this having more charge. So the region where the electric field is 0 is going to have to be somewhere over here to the right of this charge. So notice that although this is a mathematical problem, I've spent a lot of time thinking about it conceptually. And I know now that the region of 0 field is somewhere over here. So I go through this logic. And now what I'm going to do is I'm going to do some math. So essentially what I'm doing is I'm choosing a spot from wherever I'm picking to this spot I'm going to call a radius r. And since this is 4 meters further away, I'm going to call this r +4. So I end up having the electric field caused by the positive 4 charge, it looks like this. K times Q over R squared is the general formula for electric field from a point source. So it's K times 4Q over R plus 4 meters squared. And then over here it's K times 2Q over R squared. So, and I know that at a certain point, these two electric fields would be equal, and I'd set them equal to each other. So the K and the Q cancel out. So I'm left with 4 over R plus 4 squared equals 2 over R squared. So I now move over here, end up doing some algebra by taking the square root of both sides, and I get that R is at a position of 9.66 meters. So in this case, 0.41 R equals 4. So hold on, I did not bring my calculator with me. Give me a sec here. So 4 divided by 0.41. Oh, I got a little bit different answer. I must have rounded or something like that. So again, equals about 9.66 meters. So somewhere 9.66 meters to the right of this location. So hopefully that makes sense as to how we would solve that.